Now let's suppose that we have a vector field f of x, y, z equals, so its component functions are p of x, y, z, q of x, y, z, r of x, y, z. And let's see what happens. So let's make another assumption here. Let's suppose, so such that p, q, and r, these component functions, all have continuous second partial derivatives. All right, so continuous second partials in all different combinations, all the different combinations. We'll assume that they're all continuous. So this tells us a few things. Number one, p, q, and r must be differentiable, at least twice differentiable, if their second partial derivatives are going to be continuous. So we're kind of implicitly stating that they must exist, right, before we say they're continuous. And therefore, that means the vector field is smooth, differentiable, whatever you want to say. So what we would like to do in this example, this video, is compute the divergence of the curl of this vector field. Okay, so we want to compute, so this is to do, right? We want to compute the, like I said, the divergence of the curl of this vector field f. Now, let's keep in mind what these operators are doing. So just for the sake of remembering, the curl takes in a vector field and gives back a vector field. So this is an operation. It's defined on R3, of course, because it's defined by a cross product. So for us, we're kind of living in Calc 3 for the moment. When we have stuff happening in 2 dimensions in R2, we can, kind of extend to R3. But anyway, so the curl is a operator that sends vector fields to vector fields, and the divergence is an operator that sends vector fields back to functions, right? And remember, before we got any of this, we also had this gradient operator, and the gradient sends functions to vector fields. So there's kind of this hierarchy where you can go from a gradient, you can take a function to a vector field. Curl keeps your vector fields as vector. It changes them, right? But it takes a vector field to another vector field. And divergence takes you back downstairs, if you want to think of it that way, from a vector field to a function. Okay? So the whole reason for reviewing this is before you try to compute anything, you have to make sure that the thing you're trying to compute makes sense, right? So what do we have here? We have a vector field. We apply the curl to it. We apply the curl. We still have a vector field, right? But now we take that new vector field and we plug it into the divergence, and so we're going to get back a function, right? And so not only does this make sense, but now we know that whatever this is, this object, this mathematical object, should be a function, okay, just by thinking this through. Let's actually do it now. So again, our f is just, I'll write it very simply in its component form as PQR. We want to compute the curl of this vector field. So, or we could just write down the formula for this, because we in a few of these lecture videos, we have worked out the formula for the curl. So let's just write down the curl of f in its component form here, and I'll even use lazy notation in terms of the derivative. So the curl of the vector field is going to be, and I'm going to work this out in my mind because it's easier for me to remember the determinate definition of this thing, but this is going to be dy dy minus dz dq in the first component, and then the next component is going to be what? It's going to be dz dp minus dx dr. Okay, and then finally the last one, this one I never forget, this one is dx dq dx minus dp dy, right? And so there's the curl written out in this kind of shorthand derivative notation. And what we would like to do now is compute the divergence of this vector field. So the divergence of the curl of f, that's the question. Remember, the divergence is the gradient operator, or the del operator, so dx, dy, dz in this notation, dotted with our vector field. This is our vector field, right? So dyr minus dzq, comma, dzp minus dxr, comma, dxq minus dyp. And when we take the dot product, what's it going to do? It's going to apply the x partial to the first component. It's going to apply the y partial to the second component. It's going to apply the z partial to the third component, and then it's going to sum all of these up. It's going to add them up. Okay, and that's how we get a function back. So let's do it. This one's going to give us, now I'll write this out in all of its complete glory here. So this one's going to be d squared r dx dy. So the y derivative has to remain the closest one here, right? Minus the next derivative is going to be d squared q. This one's going to be dx dz. Okay, then we go to the next component. So let's color code this. All of this is the red. So that's from the first derivative, the first component here. All right. The next one is going to be plus d squared p, and this is now dy dz. Remember, the one to the right is actually the closest to p. That's the one that hit p first. Minus the next derivative is d squared r, and this is going to be dy dx. Okay. And if we're going to color code this one, then this one becomes green, right? And so we go to the next one. Plus, finally, we have d squared q. Now it's going to be dz dx, all right, minus d squared p. This one's going to be dz dy. And let's color code this one as orange because that's where it came from. And finally, we want to add these up. Okay, anything that we see that looks, similar, we want to add these up. And at this point, we go back and we remember this assumption that we made, this extra assumption or hypothesis that our component functions of our vector field have continuous second partial derivatives. And every time we read this in this class, at this point, especially in the semester, we should hear a ringing in our ears that reminds us of Chloros Theorem, right? So Chloros Theorem says that in this scenario, the mixed second partial derivatives are equal, okay? So let's see if we have Chloro anywhere in sight. Well, we do, because we have d squared r dx dy minus d squared r dy dx, okay? So I'm going to make that 0 by Chloros Theorem. Then we have minus d squared q dx dz plus d squared q dz dx. Again, the signs are opposite, the orders are reversed, but Chloros says, who cares? Those are the same, right? Those are equal by Chloros Theorem. And then finally, the only ones left are d squared p dy dz and minus d squared p dz dy. Again, order switched, doesn't matter. Chloros Theorem says they're equal. And after all of this, what we get is that the divergence of the curl of generic vector field f, right? This is for any vector field f then that satisfies our hypothesis. This is always equal to 0, and notice this is a 0 with no hat. This is the 0 function. Okay, and so this is always going to be true. Divergence of a curl, if the vector field is somewhat nice, is always 0.